Hello and welcome back to Calculus 2 for one last time. Yes, this is it. It's the end of the journey, right? 10.3 Calculus in polar coordinates. So we've learned polar coordinate points, right? Coordinates. We learned functions last time, how to graph functions, and now it's time to apply calculus. We've seen some of the graphs, let's say, last time. We've seen cardioid, right? It had a fairly simple equation. I believe it was r equals 1 minus cosine theta. I believe that was the equation for this cardioid. It was going through 1 and -1 and -2. I'm not 100%, but I think that's it. So now, if you look at this, right, there are two features of this. One is that you can draw tangent lines, right, at a point. That means if there is a tangent line, there is a slope that is related to the derivative. And also, you can color the inside, which means the thing has area, which you can compute using integrals. So the goal for this section is to cover those two things. How to find the area using integrals, and how to find tangent lines. We know that tangent lines measure change, instantaneous. This could be the path for the particle and particle accelerator or whatever. Obviously not, but you know. So we are going to look at derivatives and integrals to find area. So the first order of business is derivatives. Recall from previous class that x is equal to r cosine theta and y is equal to r sine theta. This was conversion between x and y. When I say derivative, I'm looking for dy dx, because once I plug those values, x and the y, right, I am getting the slope of the tangent line. So we need to develop a formula which will help us find this derivative. So I'm going to start by writing dy dx, and then I'm going to augment this with d thetas. So now we plug in the derivatives. Observe that I have dy d theta in the numerator. That's the one on the bottom here. And when I start taking its derivative with respect to theta, keep in mind that r is a function of theta, so you have product rule there. That means copy the first times derivative of the second plus copy the second times derivative of the derivative of the first, which is r prime. Now these r's are functions of theta. We have the same thing happening in denominator. I'm trying to log into the textbook and I have to go and solve all of these. So the derivative of the x d theta is copy the first, derivative of the second, plus copy the second, derivative of the first. So finally, to derive this dy dx, we are going to say r prime is f prime of theta times sine theta plus f of theta cosine theta divided by f prime of theta cosine theta plus f of theta sine theta. This is the formula to take the derivative when you are given polar graph. Now, I argue that this is much easier to learn how to derive than to memorize. The negative should be here. Yes. It's a negative. Yep. So now we can find the tangent lines at these values in the problem. So let's say you have your cardioid problem and you want to find the tangent line at theta equal pi over 4, where f of theta, which is r, is equal to 1 minus cosine theta. So to find the tangent line, you are going to plug everything into equation above and solve it. So you have that your f of theta is 1 minus cosine theta, and you need f prime of theta, which is sine theta. dy dx is equal to f prime, which is sine theta, times another sine theta, plus 1 minus cosine theta, times cosine theta. I am plugging everything in the formula above. F prime for f prime, f of theta for f theta. And then we'll plug in pi over 4 eventually. Now the denominator, f prime, is sine theta times cosine theta minus 1 minus cosine theta times sine theta. I generally like to work out algebra as much as I can before I start plugging values in. Which cosine sine theta? Plug in. And then the cosine was there. Copy. Minus. Right? So we plug everything in. Try to simplify algebra a little bit. Sine squared theta plus cosine theta minus cosine squared theta over sine theta cosine theta minus sine theta plus sine theta cosine theta. I like trig identities, so for me this is more fun than actually plugging in pi over 4 and grinding through 5,000 of these. I know that cosine squared minus sine squared is double cosine, cosine 2 theta. So if I if I take the negative out, I will have cosine theta minus cosine 2 theta. So these two are giving me this, but they're sine minus cosine. I need cosine minus sine, which means I have to pull out the negative, and that's how we get the negative in front of the cosine 2 theta. So that's how we get the numerator. Denominator has this, and they add. When those two add together, you get 2, right? Yes. So you will get sine 2 theta and then minus single sine theta that is there. Guys, you don't have to do any of this stuff. You can just go here and plug in pi over 4 and grind through that algebra. I like to do this because I have less calculations. No, it's cosine squared minus sine squared. and I factored out minus sine. There are no steps. The formula is cosine squared minus sine squared is this. Yeah, I can just write the formula. That's all I can do. That's all I can do. Now, when we are plugging in pi over 4, the derivative becomes m, slope. We have cosine of pi over 4, looks like a 9, 4, minus cosine 2 times pi over 4 is pi over 2, divided by sine pi over 2 minus sine pi over 4. Cosine of pi over 2 is 0. Cosine of pi over 4 is root 2 over 2. Divided by sine of pi over 2 is root 2 over 2. And, no, sine pi over 2 is 1. Oops. Sine of pi over 2 is 1 minus root 2 over 2. First order of business for me to simplify this is to multiply top and bottom by 2, which will give me root 2 over 2 minus root 2. And then rationalize to get square root out of the denominator. So 2 root 2 plus 2 divided by, which is 4 minus 2. Factor out 2 on top. Bottom is 2. They cancel. That's what I said. Please pay attention. And we have our slope, root 2 plus 1. Now, if you are, crazy for decimals and so on, you can go and put 2.41 if that makes you happy. So now, what you have is the slope for your tangent line. You need your x, you need your y, and you are on your way, right? So what do you have? You have theta is pi over 4, and you have r is 1 minus cosine theta. So conversion formulas for x and y are cosine theta. R is 1 minus cosine theta times cosine theta, and theta is pi over 4. So here we go, computing stuff again, right? So how much is x? It's going to be 1 minus root 2 over 2, everything times root 2 over 2. Because when you plug in pi over 4, cosine of pi over 4 is root 2 over 2. This gives us root 2 over 2 minus a half. because root 2 times root 2 is 2 over 4, and then cancels to a half. So now I have my x value, and for the y value, I have r sine theta, which is 1 minus cosine theta times sine theta. We plug in again pi over 4 for each theta. Y equals, and this equation gives the same value, root 2 over 2 minus 1/2, because it's the same calculation. Y equal mx plus b. Y is root 2 over 2 minus 1/2 equals m was root 2 plus 1. X root 2 over 2 minus 1/2 plus b. And there's your b. Fun stuff. So root 2 over 2 minus 1/2, and now we FOIL everything. So I'm going to FOIL and bring it to the left at the same time. So root 2 times root 2 is root 4, which is 2. So that's going to be 2 over 2, which is 1, so negative 1. Plus root 2 over 2 minus root 2 over 2, and plus 1/2. All of that is b. Half and half dies, this and this dies. B is root 2 over 2 minus 1, I hope. Tangent line. There we go. Equation for the tangent line at pi over 4. Now I'm going to strongly suggest you to redo this problem on your own when you know, at home at some point. To get you, this is just nasty trig calculations. There is no Calc 2 in any of this. This is taking Calc 1 derivatives with the product rule to create the formula, and then plug into the variables. You know the procedure for tangent line from Calc 1. So you have to be careful here that thetas are given to you and r's are given to you, but you need x's and y's. So usually where you students get stuck is this portion here. I have m. Where the hell are my x and a y? Because all I have is theta equals pi over 4. Well, you have conversions that link theta to x and the y. So as long as you learn and know those conversions, you know that, right, line is y equal mx plus b. You need that x, you need that y, you have m, so you can compute b. So this is a standard Calc 1 problem that you are now doing in coordinates, which you learn in Calc 2. A lot of trig creeps in, as you can see. As I said earlier, this derivation that I did, simplification that I did, is not necessary. I like to do that because I love trig identities, and clearly it's much easier to compute 4 values than to compute, what is this, 8 values, right? And then all the addition and subtraction and so on. So, you know, there's always a trade-off, never a free lunch, right? So that's how we deal with the derivative. And the derivative formula that we are using for polar coordinates is this. Now, I could argue that this problem, this particular problem, might be easier in x and y coordinates if you cast that back into x and y and use implicit differentiation to solve a problem. But you've seen a flower yesterday, right? The graph, and you've seen the crazy expression that that has in x and a y. Now imagine grinding through those product rules and chain rules in implicit differentiation. Well, that's crazy. So I chose a relatively short example, I would say, to demonstrate use of the derivative in finding the tangent line. Grind through this problem and try another one so that you can just get a hang of the calculations, right? We are also considering area within polar graphs, which is what I shaded in green at the beginning. Now the formula that we are going to use to calculate areas is area equals 1/2 integral alpha to beta of f of theta squared d theta. Why are the limits alpha and beta? Because, yes, we have d theta, it's angle, so we have to have angles as input. Now, if you are wondering if this dimensionally makes sense to be area, it does, because d theta doesn't have a dimension to it. It's not a unit, it's not length. So angle is a ratio of two lengths. Therefore, it has no unit. Yeah, we say radians and degrees, but those are divisions. They're not a unit of length like inches or meters or centimeters, anything like that. So this d theta does not contribute towards dimensionality of the problem. All of your dimensions, which for area is 2 dimensions, are right there, which is that r squared. And if you're thinking about equation of the circle, right, the area of the circle is pi r squared. You are getting your pi from limits because this is going to be pi over 4 and stuff like that. So you're getting your pi from the limits and you're getting your r squared from the integral. Pi r squared, we know that's the area of the circle. That being said, prove the formula for area of the circle. Let's say you are, tutoring a middle schooler, right? And this pops up, area of the circle, and you tell the kid, okay, area of the circle is pi r squared, and he goes, why? Oh, yes. All right, let's see. In polar coordinates, your circle will have equation r equals some arbitrary radius r, which could be 3, 5, whatever it is. So now circle in polar coordinates has that equation. We all understand that the circle starts at 0, goes all the way around to 2 pi to get the entire circle with the radius that you draw, right? That radius you draw on x-axis swipes all the way around and ends up again at the x-axis, positive x-axis. So now to calculate the area, you have 1/2, 0 to 2 pi, because you want the entire circle of r squared d theta. The function that we are dealing with, always remember, guys, always remember that r is f of theta. R is f of theta. So when I have f of theta squared, it's actually r squared. So now lowercase r, which is the radius, which is the variable, we use arbitrary parameter, capital R, to denote that can be any number for radius. Once we integrate this, we get 1/2. Variable that you are integrating is theta. R squared is a constant. You get to copy R squared and then put theta 0 to 2 pi. And you quickly see what's happening here. 1/2 R squared, 2 pi minus 0. One-half and 2 pi cancel, and you got your pi R squared. So this is the proof that area of the circle is pi R squared, and we use the formula. But now I want to use this formula on the cardioid we just had. I want to know what is the area inside the cardioid. The area shaded in green. Well, first so area equals question mark. First we observe that I want the whole object. That means 0 to 2 pi, and those are your limits. I will also cover very soon, so we might stay 5 minutes over or so, something else, but let's immediately calculate this area. 0 to 2 pi, 1 minus cosine theta, everything squared d theta. Hello, half-angle formulas and everything else we learned, right? We have 1/2 integral 0 to 2 pi, 1 minus 2 cosine theta plus cosine squared theta d theta. When you expand everything, don't forget the middle term as you are squaring this out. And what you see, that last term over there, cosine squared, is going to use the equation, right, to simplify it. So we have 1 minus 2 cosine theta plus 1 plus cosine 2 theta, everything over 2, close parenthesis d theta. We can integrate. We have basic integrals. Integral of 1 is going to be theta. Integral of cosine is positive sine, so minus 2 sine theta, plus integral of 1/2 is going to be theta over 2. And integral of cosine is sine, but remember you have a 2 over there, so plus 1/4 sine 2 theta, computed from 0 to 2 pi. This one? No. Integral of cosine is positive sine. Derivative of cosine is negative sine. So now, observe that 0 doesn't work anywhere because no cosines. And then 2 pi also doesn't work in sines because there are zeros everywhere. So the only thing that survives here is 2 pi plus 2 pi over 2. Everything else dies. Again, when you plug 0 in any of these terms, they're all 0. When you plug 2 pi into sine theta, that's 0. And also sine of 4 pi is 0 as well. So this is all that survives. This cancels here. And altogether 3/2 pi. 3/2 pi is the area of the entire thing. Roughly 5, right? 3.14 times 3 is about 10, divided by 2 is about 5, which makes sense. What makes problems interesting is not figuring out the entire area, but figuring out either portion of the area, like one petal of the flower, or one portion of this graph. And then tomorrow, even more interesting, is when we have the area between two objects. Flower in the circle, circle with a flower, cardioid in a flower, and all of these kind of things. So the last thing that I really quickly want to look at is the same cardioid graph, but this time I'm just interested in this much. What is the area in the first quadrant? Guys, calculations are going to remain the same. What changed here are limits. You get to graph this much of the cardioid by working out the integral 0 to pi over 2. The rest of the problem stays the same as before, 1 minus cosine theta squared d theta. All of the calculations and the guts and everything in there that we did, all of this work that you see here is the same. We are going to use pi over 2 in this line rather than 2 pi. So it's the game of limits. I could also ask you, what is the area of one slice of pizza pie? Right? You know that the large pie is cut into 8 slices. How much is the area of one pizza slice? It is definitely going to be 1/2 integral 0 to pi over 4 of whatever the radius of the pizza is. What's the radius of the pizza? 12 inches? So 12 inches squared d theta. You are calculating the area of a single slice using this integral. Note that your limits of integration are 0 radians and pi over 4 radians because you are calculating area of a single slice. Now you could, for 3 slices, go from 0 to 3 pi over 4, or you can just triple this one because it's symmetric, right? Each slice is the same if the person who works at the pizzeria is OCD enough. The last thing I'm going to draw tonight is the flower. And I believe this is the cosine one. R equals 2 cosine 2 theta. If anyone has the calculator in Polar right now, just graph the function I wrote to make sure that you actually get this flower. Actually, no, I can check. Yeah, this is good. You don't have to check. I said you don't have to check. Okay, good. So let's say I want the, now this is very tricky, guys. I want the area of one petal. What do you think your limits of integration are? Yes. Correct. Negative pi over 4 to pi over 4. Now, how? Why? Well, you have to understand that the first point when your angle is 0, you get this point, which is actually in the middle of your picture, right? So having a first point to be right here tells you that there is the angle this way and the angle that way that we have to have in order to get both halves. Now, this being also symmetric, you can actually calculate 0 to pi over 4 and double it, but that could backfire. So now, why are these pi over 4s? Well, the way I like to look at these things is, how many equal segments do I have? So there is the top of the first flower, of the first petal, then there is the right of the second, and then the left of the second, and then the top of the third, and the bottom of the third. I count 8 of them. So pi over 4 has to draw one of them. One more time, I'm going to use a finger, right? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 of these because my dot started there. So it draws this much, and then actually goes here, draws this, and goes there, and goes there, and goes there, and goes there, like that. That's how it goes. So it starts there, goes here, goes there. That's, if you do it on the calculator, that's how it's going to follow it. Now, observe that it actually ended here. So when you have negative pi over 4, that's when it's going to start going like that. And then unwrap and come back there. You have to sit by the calculator and punch these things over and over and over again to learn how these things work, because I can't teach you any of this stuff.
Would that be pi over 4 and 8 pi over 4?
Yes, so that's why we have those limits. Now for the same graph on sine, that it's like this. It's a different story now. And this is where we end. How many symmetric things you have? You have 4.
4.
So because you have 4 now, your 2 pi, exactly, your 2 pi over 4 is pi over 2. So area is 1/2 integral 0 to pi over 2 sine theta, sorry, sine 2 theta, because we have 4 petals, d theta, sine 2 theta for the function, squared. Don't forget the square there, guys. That's function squared in the formula. And again, if you're trying to compare the two pictures, which I can bring now, the top picture has 8 symmetric things around, the bottom picture has 4. So 2 pi for the entire thing goes up, right? And yeah. Cool? So we'll do more of these integrals tomorrow. More interesting stuff than this. Yes?
I get between 0 and pi over 2, even though it doesn't like really show on there. I know you get pi over 2, but how do you get 0?
Well, you start drawing at 0, right?
Yeah.
So theta equals 0 is the first value that you would put on the chart when you want to draw the graph.
Okay.
So theta equals 0 gives you sine of 0. Sine of 0 is 0 times 2 is 0, so it's origin. So that's where the 0 is.
Okay.
And then we calculated over here 4 same things when we get pi over 2. So this one should draw and finish at pi over 2.
Okay.
Right? Because this shows when it goes and loops back on it.
Okay.
Right?
I have a semester project I want to discuss with you about.
All right.